Hello guys, and welcome back to my YouTube channel. In this video I'm going to be talking about substitution reactions. We're going to be going over SN1 in comparison to SN2 reactions. We're going to be comparing their mechanisms, the nature of their electrophiles, hence their substrate, the thing that will be delta plus, and the thing that's getting attacked by our nucleophile, which will be the third thing I will be discussing. And number 4, the leaving group. Alright guys, first things first, let's talk about the mechanism of an SN2 reaction. So here, a nucleophile, so the thing with the electrons, the thing with the currency of organic chemistry, our nucleophile, is going to attack something electrophilic on the other molecule. So the electrophilic thing is going to be the carbon that is attached to our leaving group. Since opposites attract, the nucleophile is going to take its lone pair, so its electrons, the currency, and it is going to attack the delta plus carbon with the leaving group. And since you cannot break the octet rule, every 2 in on a neutral carbon must be reciprocated with a 2 out. So what happens is the nucleophile comes in and will now be attached to the pink carbon. And the stereochemistry flips. So R2 will move from the left-hand side of the original substrate in the starting material to the right-hand side. You can think of this as an umbrella flipping inside out. So this is my umbrella. And heavy winds, boom, it's going to hit the umbrella. Pretend that the heavy winds would pop off its initial stick. And you would now get a green stick and an inverted umbrella. So going back to our original substrate, if you chop it in half vertically, R2 is on the left-hand side, and the leaving group is on the right-hand side. We can see that in the products, we get the opposite. The nucleophile is now on the left-hand side, and R2 is now on the right-hand side. Let's just clean this up a little bit, and we will summarize everything we just seen here. So in summary, what did we get? An SN2 reaction. A nucleophile attacked an electrophilic carbon with a leaving group, and the nucleophile forced the leaving group to leave. So this means that the reaction was one step. So this was a one-step reaction. But it was the action of the nucleophile attacking that carbon that forced the leaving group to leave. So this reaction depends on 2 things. It depends on the concentration of the nucleophile, but also the concentration of the substrate. So since it depends on 2 things, this reaction is referred to as an SN2 things. It's all about the mechanism. So the mechanism depends on both the concentration of the nucleophile and the substrate. So that is what an SN2 mechanism looks like. So now let's compare this to an SN1 mechanism. Guys, now let's talk about SN1 mechanism. Step 1 is a little different. In the SN1 mechanism, step 1 is the leaving group takes those 2 electrons in the initial C leaving group bond, and it goes peace out, and it leaves. So that means the carbon loses a bond. So initially, if carbon has 4 bonds, when it is neutral, if it loses a bond, well, it loses an electron it was sharing in that bond. So it will become cationic. So you still have the 3 R groups, but now that carbon is cationic. This means its hybridization also changes. Now there's only 3 groups surrounding it, and they will be oriented in the trigonal planar. Where planar, if you think a plane, is a flat thing. So you think flatness. This is very important. So step 1 was the leaving group leaves. Now step 2 is you toss in some nucleophile And since opposites attract, the nucleophile will be really attracted to the carbocation. So it's going to attack it 2 in. You may ask why is there no 2 out? Well, that is because the carbon is in a deficit of electrons. You only go 2 in, 2 out on a neutral carbon. So here, since the carbon is cationic, you would just go 2 in. And what you would get is the nucleophile makes a bond to that carbon, and it is neutral in the end. But here, we do not see an inversion in stereochemistry, and the reason for that is due to the hybridization, the sp2 trigonal planar hybridization of the intermediate after the leaving group leaves. So because the intermediate state is flat, that means the nucleophile could attack from the top or the bottom, and you would get a racemic mixture. So you're going to get 50% of one and 50% of the other. So this means that you would get both. This is called a racemic mix. In other words, you can just draw a straight line from the nucleophile to the initial carbon with the leaving group, and that would be your answer. So this reaction, yes, was 2 steps, right? We had step 1, where the leaving group left, and we had step 2, where the nucleophile attacked. But the rate only cares about the first step, because think, the leaving group is usually a bigger, bulkier group. It's going to take some effort for the leaving group to leave, so this takes a little bit of effort. So the slowest step is going to be the first step, the slowest step. It takes some effort for that leaving group to leave. So that means we only care about the concentration of our substrate. Concentration. So that means we only care about the concentration of one thing. The concentration of one thing. Therefore, this is referred to as an SN1. It has to do with the mechanism. So now, throughout this video, we're going to be making a little table. In our table, we're going to put the differences. So for an SN2 reaction, the reaction is going to be 1 step. SN1 reaction, the reaction is going to be 2 steps. So now the next thing we're going to talk about is the substrate. So the substrate for an SN2 reaction, where we have a nucleophile attacking some carbon with a leaving group. The carbon is usually going to be referred to as either a 1' carbon or a 2' carbon. 2', where primariness refers to how many other alkyl groups the carbon with the leaving group is attached to. So here, this blue carbon would be attached to 1 other alkyl carbon, whereas the carbon that is 2' would be attached to 2 alkyl groups, therefore 2'. For the case of a nucleophile attacking a 1' carbon, this reaction is going to be very, very, very fast. This is the best. When a nucleophile attacks a 2' carbon, this is, yes, okay, but it is not as good as the 1' carbon, and this is due to the increase in steric hindrance. It's going to be harder for that nucleophile to come in and punch that blue carbon in the face, because you could think of these alkyl groups as little friends that are going to protect those electrophilic carbons. And you almost never have, I can't think of an example where you have a nucleophile attacking a 3' carbon, because if you want to think about the nucleophile and the electrophilic carbon as 2 people in a relationship, let's say the blue carbon is a girl, but the nucleophile is a boy, and he just cheated on the blue carbon. The friends, let's say they were all at the club, the 3 friends of the blue carbon, the girl, are going to get in the way between the guy and the girl. If the guy tries to come and talk to this girl, the friends are going to say, you ain't talking to my girl today. They're going to come in and they're going to block that guy. They're going to say, no, you cannot talk to our friend. She is hurt and you are rude. So here, this usually will not proceed. I can't think of an example. I don't want to say never, ever, ever, but I cannot think of an example where you would ever see this. This does not occur. Does not occur. This is bad. And this is due to steric hindrance. So for an SN2 reaction, the best case is the substrate is 1'. Second best would be 2'. Whereas the substrate for an SN1 reaction, it's a little bit of a different argument. The substrate for an SN1, we want to be 3'. So we want this carbon with the leaving group to be 3'. And this is because, well, the first step is that the leaving group leaves, right? So it takes us 2 electrons and it goes peace out. And we get this carbocation. So what makes a carbocation stable? Well, the more alkyl groups that are attached to this carbocation will stabilize this positive charge. Because these CH3 groups, or CH2 groups, they're going to be electron rich, but they're not going to be greedy. So they're going to be little electron guns, and they're going to shoot electrons into the carbon that is in an electron deficit. So this is a favorable action. So therefore, a 3' carbocation is going to be more stable than a 2' carbocation, which is going to be way more stable than a 1' carbocation. Where SN1 reactions will favor the 3' carbocation. So since the carbocation is very, very stable when you have a 3' carbon, the leaving group will leave faster because it's not worried about what it's going to leave behind. It's going to leave behind something that is happy. So since it's going to leave behind something that is happy, it is not afraid to leave. For example, if you were in a relationship with somebody and you knew that they are a quite stable, confident person, you wouldn't be afraid to break up with them because you know that they would be happy on their own. You don't need to worry about them as a single person. So going back to our table, for an SN2 reaction, the substrate, we want that carbon to be 1' is best. For an SN1, we want the substrate to be a 3' carbon. This is best. N2 is okay. So now the third thing we will be talking about is the nucleophile. So for an SN2 reaction, remember, going back to our mechanism, this reaction depends on both the concentration of the nucleophile and the substrate, because this reaction is one step where the nucleophile goes 2 in, which forces the leaving group to leave 2 out. So that means that the better the nucleophile, if you increase the ability of the nucleophile, this is going to increase the speed of the reaction. Therefore, in an SN2 reaction, strong nucleophiles are going to be the best, because a strong nucleophile is going to be able to come in and better attack that delta plus electrophilic carbon. So let's go over what an excellent NU is. So an excellent nucleophile is going to be some atom that is negatively charged. And this negative charge cannot be stabilized, because if you can stabilize something, stability is always inversely proportional to reactivity. So if something is stable, that means it is unreactive. So you do not want to be able to stabilize this negative charge. So here, an excellent nucleophile would be something like a methoxy group where the oxygen is deprotonated. A good nucleophile would be some atom with a negative charge, but this negative charge is not as reactive as an excellent nucleophile. Here, this negative charge can be resonance stabilized. Therefore, you can think of this as part of the time this oxygen doesn't even have that negative charge. So half the time it doesn't want to be a nucleophile, and half the time it does. So some atom that is minus, but the minus can be stabilized. Whereas for an excellent nucleophile, we have some atom that is negatively charged. So a bad nucleophile, or in other words, a weak nucleophile, is just going to be some atom that still has nucleophilic properties. So it still has lone pairs, but it is neutral. So some atom with lone pairs, but it is neutral. So now for an SN1 reaction. So if we go back to the mechanism, a nucleophile, wait, no, it doesn't matter. It doesn't matter. We don't care. We don't care about the nucleophile, because the rate determining step is the leaving group leaving. That's the first step of our SN1 reaction, is the leaving group leaves. Therefore, once the leaving group left, that was the hardest part. For us to get this carbocation, the hardest part was the leaving group had to leave. So the rest is easy. We're on the downhill part of the slope. That means when the nucleophile comes in, it doesn't really matter if it's a good, bad, or weak nucleophile at the end of the day. It's still going to be able to attack this carbocation. So it's more about the SN2 reaction. So since the SN2 reaction favors a strong nucleophile, SN1 reactions, you could think, favor the weak nucleophile. But it's more of the fact that a weak nucleophile will never proceed via SN2. Or, I once again hate to say never, but will most likely not proceed via SN2. Therefore, weak nucleophiles will proceed via SN1, because once again, it doesn't really matter the strength, because something that is negatively charged or something that is neutral with lone pairs is still going to want to attack a carbocation, especially since it's flat. This is a very easy thing to attack. You can think that there's a decreased steric hindrance to this action. It is easy for the nucleophile to go, hey, 2 in, not even a 2 out. I don't need to push anything out. And I just get my final product. So back to our table. For an SN2 reaction, the nucleophile, we want an excellent nucleophile. And for an SN1 reaction, we can proceed with weak nucleophiles. It doesn't really matter because you have that 3' carbocation, the leaving group already left. We don't really care about the concentration of the nucleophile, or we also don't care about the strengthening of the nucleophile. It's more about the fact that weak nucleophiles just are not going to proceed via SN2, so they can proceed via SN1. So the last thing we have to talk about is the leaving group. So let's talk about the SN2 versus the SN1. So both an SN2 and an SN1 reaction, you're going to want a good leaving group. The leaving group, we want to be good. Leaving group. So essentially for both of these reactions, it is going to be favorable to have a good leaving group. So what makes a good leaving group? It would be something that can leave that will be stable once it leaves. So a good leaving group is going to be able to stabilize that negative charge. So how do you stabilize a negative charge? This could be through resonance or induction or the atom or the orbital. Go back to one of my previous videos where I talk about this, if this does not ring any bells. But more specifically, an SN1 reaction, we really care about how good that leaving group is. And the reason that is because the mechanism depends and the rate depends on how good of a leaving group that is, because the better the leaving group, the more likely it is to leave. So that means the faster the reaction will proceed. So here it is, best case would be an excellent leaving group. And here it really, really, really matters more than an SN2, even though a good leaving group is good no matter what, because the rate solely depends on the concentration of that leaving group in the SN1. So going back to our table, you want the leaving group to be good / excellent. But for an SN1 reaction, you really want it to be excellent. because the rate determining step is when the leaving group leaves. Alright guys, that brings me to the end of this video. I went over the theory behind SN2 versus SN1 reactions and the main differences that we're going to see. I will do another video where I will go over some examples of what this looks like, proceeding via an actual question. But I hope this video helped. Make sure to leave a like, comment, save, and/or subscribe to my channel if you like my content. And I hope you have a good day. I will also be posting an eliminations video later this week. Have a very busy week. It's actually like 4 a.m. in the morning right now. I got up to film this. I have to do a group meeting. I have to present this poster presentation. Now I'm just blabbing. You don't really care. But yeah, hope you have a great day. And let me know if you have any questions.